Welcome back to this next video in which we are discussing linear independence. Okay, so in this final video what we're going to do is have a look at some examples of sets of vectors for which we can say whether they are either linearly dependent or linearly independent. Okay, now we're initially going to do this for an abstract vector space, okay, so a general vector space over some general field, capital F, and we're going to have sets that will be relevant in any vector space. But then what we're going to do is we're going to go to a more concrete example, our favourite example, R3, and we'll have a look at some examples of linearly dependent and linearly independent sets of vectors there. Okay, so the first thing then that I want to talk about is in a general vector space, so we're still dealing with our general vector space V over F, okay? In our general vector space, there is a way of absolutely ruining a set's hopes and dreams of being linearly independent. Okay, so I want to show you this way that you can absolutely ruin the chance that a set of vectors has of being linearly independent. So if you have a set of vectors, so we'll have our set of vectors from our vector space here. So here it is, v1, v2, and we'll go on and on all the way up to vm minus 1. Okay, and I'm going to add in an nth vector here, and I want to shatter this set of vectors' dreams of being a linearly independent set of vectors. There is one vector that you can add in that will absolutely do the trick, and that's the 0 vector, a very special vector in the vector space. So this is what I want to show you now, that if you add in the 0 vector into a set of vectors, that set of vectors is absolutely not linearly independent. So any set of vectors that contains the 0 vectors has not a hope of being linearly independent. Okay, right. So let's now prove, or at least gain some understanding as to why this set of vectors that contains the 0 vector cannot possibly be linearly independent. Okay, right. So let's consider what a linear combination of this set of vectors will look like then. So it will look like c1 times v1 plus c2 times v2 plus all the way up to cn minus 1 times vn minus 1 plus cn times the 0 vector here. Okay, so this is what a linear combination of this set of n vectors actually looks like. Okay, now, if we wanted to investigate as to whether this set of vectors is linearly independent, we need to look at the linear combinations of this set of vectors which actually give as the answer the 0 vector. And if it's going to be linearly independent, it needs to be the case that there is only one linear combination that can possibly give the 0 vector, and that's the trivial linear combination where all of these coefficients c1, c2, cm minus 1 all the way up to cn, they are all equal to 0. Okay, that has to be true if this set is going to be linearly independent. Now, I can instantly say that that's not going to be true, okay? There is going to be a non-trivial linear combination of this set of n vectors which gives us the answer, the 0 vector. And this is why, okay, we can make all these other coefficients, c1, c2, all the way up to cn minus 1, we can make absolutely all of them equal to 0. So we can make them the additive identity in the field. And we know as soon as we make them the additive identity in the field, this one will, the answer to this will be the 0 vector, the answer to this will be the 0 vector, and we'll go all the way up here, we'll have the answer as the 0 vector. So all of this together will be the 0 vector. But what we can now do is set Cn equal to any element of the field you like. Okay, and the reason you can set it equal to any element of the field you like is that any element of the field scalar multiplied by the 0 vector gives the 0 vector back again. Okay, that is one of the things that is always true in a vector space. Okay, and it follows from one of the distributive laws that you insist that scalar multiplication in a vector space must obey. So this is true for all C as an element of your field, capital F. Okay, so drawing a picture of this, let's draw a picture of our scalar multiplication composition table here. So here is our scalar multiplication composition table. We'll have all of the elements of the field down here. So all of the elements of the field have a row dedicated to them, and then we'll look at the column dedicated to the 0 vector here. Okay, so what this is saying is that you take any element of the field you like. Okay, so go for any element of the field you possibly want. Okay, if you use that element of the field to scalar multiply the 0 vector here, you will get the 0 vector back again. So this column corresponding to the 0 vector is just going to have loads and loads of 0 vectors in it. It's a really boring column. Okay, loads and loads of 0 vectors. So every element of the field will have a 0 vector in its row, which is in that position corresponding to the column for the 0 vector. Okay, right, so any element of the field, scalar multiplying the 0 vector gives the 0 vector back again. So let this equal whatever you like, basically. It doesn't need to be 0. It can be whatever you want in the field. And the answer here will still be the 0 vector. So you'll have the 0 vector plus the 0 vector plus, and then finally here you'll have another 0 vector. So you'll be adding together just n lots of the 0 vector, and of course that's equal to the 0 vector. So what I've just shown you then is that any set of vectors that contains the 0 vector is not going to be linearly independent, because it is not going to be the case that there is only one linear combination of that set of vectors which gives the 0 vector. Okay, as I've shown you here, you'll have multiple linear combinations because you can let this vary over whatever element of the field you like and get a new linear combination. Okay, so there is not just the trivial linear combination, there are loads of others that give the 0 vector. So that set of vectors is not linearly independent. We have shattered its hopes and dreams. Okay, right. And that, by the way, includes the set that just contains the single 0 vector. So if you look at the set that just contains the 0 vector on its own, that is also going to be a linearly dependent set. Okay, it's not going to be linearly independent. And the reason is that if we consider all the linear combinations of that set, it'll be all things of the form C1, 0. Okay, now whatever you set C1 equal to, let it be any element of the field you like, that will give the 0 vector. So obviously then there are multiple linear combinations, in fact all linear combinations give the 0 vector as the answer, so it's not the case that only one linear combination exists that gives the 0 vector as its answer. Okay, so any set that contains the 0 vector is not linearly independent, it is linearly dependent. It fails this criterion that there is only one linear combination of the vectors which actually gives the 0 vector. Okay, right, so there's one set of vectors then that we can always make a comment on no matter what vector space that we are dealing with. Okay, right, now what I want to do is do the converse. I want to show you sets which are relevant to all sorts of different vector spaces, which are always going to be linearly independent. Okay, so what I now want to consider is sets that only contain a single vector. So let's take a set of vectors that only contains one vector. So I should say a set that contains a vector. Okay, so here is our set now. Okay, just containing a single vector which we'll call v1. Okay, now v1 can be any element of the vector space that you like, bar one element. Okay, and there's one element that I don't want to consider again because we've already considered it, and that is the 0 vector. Okay, so don't let v1 equal the 0 vector, but let it equal any other vector from the vector space you like. My claim is that providing v1 is not equal to the 0 vector, this set is linearly independent. Okay, so if you consider all the linear combinations of this set of vectors, you will find that only one linear combination actually gives the 0 vector. So let's explore this. So linear combinations look like this, c1 times v1, so all scalar multiples of this vector v1. Okay, so my claim then is that there is only one linear combination which actually gives us its answer, the 0 vector, which is that where c1 is equal to 0 in the field. Okay, so my claim is that it's only true that c1 times v1 is equal to the 0 vector when c1 is equal to 0 in the field. Okay, so how can I prove that? We do need to prove that. There's something to prove there. Okay, we want to prove that no other element of the field that isn't 0, that isn't the additive identity of the field, when multiplied by v1 gives the 0 vector. Okay, so how are we going to prove that? Well, we'll prove it by proof by contradiction. Okay, so let's assume that c1 is some element of the field that is not 0. Okay, so we know that 0 will indeed multiply by v1 to give the 0 vector, because 0 will multiply any vector to give the 0 vector. Okay, so let's assume that C1 is some other element of the field. Okay, and now let's say that we have some other element of the field which will multiply by v1, scalar multiply by v1 to give the 0 vector. Okay, so we want to arrive at a contradiction. So let's say C1 v1 is indeed equal to the 0 vector. So how are we going to arrive at a contradiction here? Well, the way we're going to arrive at a contradiction is we're now going to scalar multiply both sides of this equation by the multiplicative inverse of C1. Okay, this is where we're going to use the fact that this is a field. Okay, in a field, all the elements bar the additive identity, i.e. 0, have a multiplicative inverse, something which they will multiply with to give the multiplicative identity 1. Okay, we'll denote this 1 over C1, which is the common notation. Okay, so 1 over C1 is some element of the field. It exists. Okay, so what I'm now going to do is use 1 over C1 to scalar multiply both sides of this. So if it's true that this vector is equal to the 0 vector, then if I scalar multiply both sides of this equation by this, I should still have an equation that's true. So what I'll now do is I'll say 1 over C1 scalar multiplying C1 times V1 is equal to 1 over C1 times the 0 vector. Now, what do I know happens if I take any element of the field and I multiply it by the 0 vector? Well, I get the 0 vector back again. Any element of the field multiplying the 0 vector gives the 0 vector back again, so I can instantly replace that again with the 0 vector. Okay, but this side is more interesting here, because I know that scalar multiplication has to obey associativity if we're working in a vector space. So what I can say is I've got a vector here that's firstly been multiplied by C1, and now I'm multiplying it by this other element of the field, 1 over C1. Okay, I know, because I insisted it was true for a vector space, that I can reassociate this basically. I can change the brackets to being like this. 1 over C1 times C1 in the field, and then scalar multiply that by V1. Okay, so if we're working in a vector space, this must be equal to this. Okay, where this is multiplication in the field. Okay, so this is the statement that scalar multiplication associates with multiplication in the field. So I've now got the multiplicative inverse of C1 in the field being multiplied by C1 in the field. Now by definition that is going to give me the multiplicative identity in the field, 1. Okay, so what I've got on this side now is 1 times the vector V1. But what's my third axiom of scalar multiplication in a vector space? That the multiplicative identity multiplied by any element of the vector space gives that element of the vector space back again. Okay, so this now tells me that V1 is equal to the 0 vector. Okay, because this side is equal to V1, this side is equal to the 0 vector. What was my initial assumption? That I had picked a V1 which was not equal to the 0 vector. Okay, so this statement cannot have been true. If V1 is not the 0 vector, then it is not true that there is any element of the field that's outside of the 0 element of the field which multiplies by V1 to give the 0 vector. I'll state that again. Okay, so V1 is not the 0 vector, so it's some element of the vector space besides the 0 vector, and C1 is some element of the field besides the additive identity in the field, then C1 times V1 is not equal to the additive identity. Okay, so it truly is true that the only linear combination then of this set containing this one vector V1 which will give the additive identity of the vector space, the 0 vector, is the one where the scalar is equal to the additive identity of the field, 0 in the field. Okay, so this is a linearly independent set of vectors. Okay, right, so that's enough of general vector spaces. What I'm now going to do is do some more interesting examples, but we're going to go from the general setting of vector spaces to a more concrete setting. We're going to use a concrete example of a vector space, and we're going to use everyone's favourite example of a vector space, which is R3. Okay, now I'll just remind you of what R3 actually is. Okay, so R3 is the set containing all 3 tuples or triplets of elements of the real numbers. So you can either arrange these as column vectors or row vectors. At this stage it really does not matter. At this stage they are just different symbols. Okay, we haven't attached any meaning to those different symbols yet. Okay, so we might as well go for column vectors here. So we'll have x1, x2, x3 here, a nice column of 3 real numbers where all of these are elements of the real numbers. So the xi's are elements of the real numbers. Okay, and the real numbers is a field algebra. It's a very complicated field algebra. It takes a lot of constructing, but it is a field algebra. It obeys the axioms of field theory. Okay, so that is R3 as a set. How then do we define addition and scalar multiplication by the elements of the field? Again, by the way, this is going to be a vector space over the field of real numbers. Okay, so the way that we define addition is that if we have 2 vectors, so we'll have one vector here, x1, x2, x3, okay, and then we have another vector which we'll call x bar 1, x bar 2, x bar 3, so this is a different vector, or potentially the same vector. Of course it could be the same vector, you can add the one vector to itself. Okay, the way you do this is you do it component wise. So if you want to add these 2 new symbols that I've created in this great big set together, the way you do it is you add x1 to x1 bar, where this is addition in the field of real numbers. Okay, so this addition here is addition in the vector space. So this is the addition that I'm defining. This is the addition that I'm assuming is already defined because it's the addition in the real numbers. Okay, then for the second component you're going to add x2 to x2 bar, and for the third component you're going to add x3 to x3 bar, and again all of these additions are done in the field of real numbers. Okay, and we show in the video on definition of a vector space, I believe, that this indeed does actually obey the axioms that we need addition to obey in a vector space, i.e. the abelian group axioms. Then for scalar multiplication, so if we have some scalar from the real numbers and we want to multiply it by x1, x2, x3, then again it's just the common sense thing. What we do is we multiply each of the components by c, but this is multiplication in the field. Okay, so when I write cx1, that means c times x1 in the field of real numbers, c times x2, c times x2 in the field of real numbers, whereas c times this meant scalar multiplication in my vector space. And again we prove in the video on definition of a vector space that this obeys the axioms that we need scalar multiplication to obey. Okay, so here is our vector space of R3. Okay, right, so let's have an example then of a linearly dependent set first, and then we'll have an example of a linearly independent set of vectors from this vector space R3. So how can we go about constructing a set that is deliberately going to be linearly dependent? Okay, well one way that we could do it is we could put the 0 vector, which is the vector where you have 0 from the field in all 3 components, but that's a way that we've already explored, so that would be a bit boring. But another way that we could do it is we could have one vector which is already a linear combination of the others, okay, because remember we proved that if a set of vectors is linearly independent, it cannot be the case that one of them is a linear combination of the others. So if we made one a linear combination of the others, then it wouldn't possibly be linearly independent. So let's do that as our first example. Okay, so let's make a set then that contains, we'll go for just 2 vectors, okay, and we'll call this set capital S, okay, and let's put the first vector in. Now, what should we have as our first vector? And I'm just completely making this up. Let's have something arbitrary. We'll have 3, and then we'll have 2 in the second component, and then 0 in the third component, okay. And now what I want to do is put in another vector, which is a linear combination of this first vector, okay, so it can be written as a scalar multiple times this first vector, okay, so why don't we just have negative 2 times this? Okay, now if we multiply that by negative 2, we'll get negative 6 as the first component, negative 4 as the second component, and 0 as our third component there. Okay, and this set of vectors that I have created here, this is now guaranteed to not be linearly independent, okay, because one can be written as a linear combination of the other. One is already in the span of the first, okay, the second is already in the span of the first. Okay, so just to prove then that there will be a non-trivial linear combination of these two vectors which will give the 0 vector, what we want to construct then is c1 times the first vector, okay, plus some c2 times the second vector here, negative 6, negative 4, 0, okay, and we want to find a non-trivial combination, so some combination that is not 0, 0, which will make this equal to the 0 vector 0, 0, 0 here. Okay, well how can we do this? Well, we know this one is negative 2 of this one, so if we let c1 here equal 2, and we let this one equal 1, will that do the job? Okay, because remember this one is negative 2 of this one, so we've got 2 lots of this one plus negative 2 lots of this one. It looks as though that would do the job, but let's just verify it. Okay, so if we scalar multiply this by 2, we'll end up with 6, 4, 0, so just multiplying all of the components by 2 in the real numbers. Okay, if we scalar multiply this by 1, of course it won't change, so we'll end up with negative 6, negative 4, 0. Okay, and then we'll add these two together. 6 will add to negative 6 to give 0. 4 will add to negative 4 to give 0, and 0 will of course add with 0 to give 0. So there indeed I have found you a non-trivial linear combination of these two vectors which gives the 0 vector, so clearly this set is not linearly independent. Okay, so let's explore exactly what that means in terms of an actual picture, okay, because we know the reason we love R3 so much is that we can picture it, we can visualize it in our minds, okay, so we have this three-dimensional grid and we can associate with all of the vectors in R3 a point in this grid, or one of the position vectors to the point in the grid from the origin, okay, so if we have this vector 3, 2, 0, let's just mark that on. So that has x component 3, y component 2, and then z component 0. And that's why I chose to make the z component 0, because it makes it nice and easy to draw. So here is our first vector that I put into the set here, or this is a picture of the first vector. Now, what does the span of this first vector look like? What does the set of all linear combinations of this vector look like? Well, of course, that's just all scalar multiples of this multiplied by all real numbers, okay? And we know how that shows up in our visualizable picture. That will just be the line that contains this vector, all the points on that great big line that contain this vector, okay? So this is the span of this vector, which I'm now colouring in here in red. So this is span of, and I suppose we should give that vector a name, but I suppose we already have a name, so I'll just put the span of this vector 3, 2, 0. Okay, and that's coloured in there in red. So basically, the problem here, the reason this set was not linearly independent, is that this one ended up being in the span of this first one. Okay, so specifically, it's negative 6, negative 4, 0. This one times negative 2, so multiplying it by negative flips it round, and then because of the 2, we've doubled its length. So this is effectively our second vector here, which will also be on that line. Okay, so that was why that failed to be linearly independent. Now let's try and actually construct a set that is going to be linearly independent, and we'll have the same starting vector as before. Okay, so again we'll start with 3, 2, 0, but this time let's put in a second vector that will create us a linearly independent set, so won't create us a linearly dependent set. Okay, now we know that providing that this second vector is not in the span of this first one, then it will be a linearly independent set, because remember we proved that if a set is not linearly independent, then it's linearly dependent, then there is a way of writing one of the vectors in terms of the other one. Okay, so if it's the case that there is not a way of writing one in terms of the other, then, well, as a linear combination of the other, then it must be the case that it's linearly independent, because if it's not linearly independent, we know that there is a way, a linear combination of the others that you can write one in terms of. Okay, so all I need to do is get some vector that isn't in the span of this one, i.e. that's not on this line. So let's pick the most easy one to add onto the picture that I can come up with, one that points directly upwards. Okay, so we'll have, what about 0, 0, 2? Okay, I could have made it slightly simpler, I could have gone for 0, 0, 1, but I want to make it slightly more interesting. So there we go, 0, 0, 2, one that points directly upwards, and you can see quite clearly that that is not on that line. Okay, so this should be linearly independent. Okay, now let's just check that our intuition in terms of the picture actually stacks up in terms of the formal definition. So we want to make sure that the only linear combination that can satisfy this equation, that it gives the 0 vector, so c1 times that vector plus c2 times this vector, must equal 0, 0. We want to make sure that the only solution to that is that c1 and c2 are both equal to 0. Okay, well, let's think this through. Okay, so if we multiply this vector by c1, what will we end up with? We'll end up with 3 times c1, 2 times c1, and then 0 in our bottom one. Okay, so just applying the rules for scalar multiplication in R3. Okay, then if we multiply this one, okay, scalar multiply this vector by c2, we'll end up with the vector 0, 0, and then 2c2, like so. Now if we want to add those two together, and I'll just firstly underline it nicely, if we want to add those two together, what will we end up with? We'll end up with 3c1, 2c1, and then 2c2. Okay, now if we want it to be the case that this is 0, 0, 0, clearly that tells us that c1 has to equal 0. I mean, you can't multiply some number by 3 and get 0 unless that is 0. Two numbers cannot multiply together to give 0 in the real numbers unless one of them is 0. So this tells us that c1 has to equal 0, and this bit down here gives us the fact that c2 has to equal 0. Okay, so that is the only possible way that you can take a linear combination of these two things and actually end up with 0, 0, 0, the 0 vector. Okay, so those two are linearly independent. With that then, we will end this video on linear independence.